In this video, we're going to go over section 6.2 from our textbook. And so this section contains important applications of the definite integral to business and economics. So first, we'll start with probability density functions. So suppose that an experiment is designed in such a way that any real number x on some interval is a potential outcome. So for example, x may represent an IQ score, the height of a person in inches, etc. Technically, we'll refer to x as a continuous random variable. So in certain situations, we can find some function f with x as an independent variable such that the function f can be used to determine probability here. And that's going to be the probability that the outcome x of an experiment will be within this interval here. And so this type of function is called a probability density function and must satisfy these three conditions here. All right, so looking at the figures here, for example, the probability that x will be in between this interval here is going to be equal to the area under the curve for this interval here. So the probability that x lies in between c and d, for example, is going to be the area under our curve for our probability density function within our interval c to d here. So let's look at an example of this. We're told that the length of phone calls in minutes is going to be a continuous random variable with the following probability density function here and shown in this figure here. Now what we want to do is find the probability that a call selected at random will last 4 minutes or less. So that is part A here. So we want to figure out the probability, and following the notation above, we would write it like this. So we want to figure out the probability that a call selected at random will last 4 minutes or less. So this means our variable t here, which is in minutes, is going to be in between 0 and 4. So we know that the probability of this guy is going to be the definite integral of our function from 0 to 4. And our function was 1/4 e to the minus t over 4. All right, we have this composition of functions here, so we know that we can use u substitution, and in that same step, I'm going to pull this 1/4 out of our integral here. So we're going to let u be equal to negative t over 4. This tells us that du over dt is going to be negative 1/4, and therefore du is going to be negative 1 over 4 dt. And so getting dt alone, we can multiply both sides by negative 4, so we get negative 4 du is equal to dt. Okay. Now, what I'm going to do here is evaluate the indefinite integral, so we're going to ignore these bounds for a moment. So we'll have 1 over 4, and then we're taking the indefinite integral of e to the u times minus 4 du, right? Because minus 4 du is equal to dt here. Evaluating this guy here, we can bring out this negative 4 in front, so these 4's will cancel. And so we're just left with the negative out front integral of e to the u du. And we know this is going to be negative e to the u plus c. Now we can take this information and then evaluate our definite integral here. And we'll keep the same bounds as this because we will change our variable of integration back to our t here. So what I mean is, starting with our original definite integral here, we want to evaluate this. We'll get negative e, plugging back our value in for u here, to the negative t over 4, evaluated at 0 and 4 here. So then we'll get minus e to the negative 4 over 4 minus negative e to the negative 0 over 4. Negative e to the negative 1 is on this side here. And then we're going to subtract out a negative 1 because e to the power 0 is 1. We have negative e here, but we're subtracting out a negative 1, so this will be plus 1 here. And so we see that this is approximately equal to 0.632. Now for part B, we're asked to find some b so that the probability of a call selected at random lasting b minutes or less is equal to 0.9. So we want to find a value for b such that this guy here is equal to 0.9. So we want to find some variable b such that the probability of a call selected at random lasting b minutes or less, so t is going to be in between 0 and b, will be equal to 0.9. So setting this up, we know that this here is equal to the definite integral of our function from 0 to b. Our function is 1/4 e to the minus t over 4. And we know that this is equal to this, so this must be equal to 0.9. So we want to find a b that makes this statement true. We know from above that taking this definite integral here, we'll get negative e to the negative t over 4, evaluated at 0 and b, and this will be equal to 0.9. Repeating the same steps as above, we'll get negative e to the negative b over 4 plus 1 is equal to 0.9. Now we'll subtract out this 1 on both sides. And now what we want to do is solve for b. So we can do so by taking the ln on both sides. Since ln and e are inverses, what we'll get on the left-hand side is, actually the next thing I'm going to do is cancel the negatives on both sides. So we'll end up with e to the negative b over 4 is equal to positive 0.1. Now, if I take the ln on both sides, I'll put this over here, we'll just get negative b over 4 is equal to ln of 0.1. Now to solve for b here, I'll multiply both sides of this equation by negative 4. So I'll get b by itself is going to be equal to negative 4 times ln of 0.1. And so this tells us that b is roughly equal to 9.21. All right. Now the next thing we're going to look at is what's called continuous income stream. So, for example, let's suppose that an aunt has established a trust that'll pay you $2,000 a year for 10 years. We want to figure out what is the total amount you will receive from the trust by the end of the 10th year. Well, we know since there are 10 payments of $2,000 each, you'll receive $20,000. Now, thinking about this in a different way, let's assume that the income stream is continuous at a rate of $2,000 per year. So we can see this in this figure here. The area under the graph of f of t is equal to 2,000 here, from 0 to t, represents the income accumulated t years after the start. So, for example, if t were to be equal to 1/4 of a year, the income would be 1/4 of 20,000. So that'll be $500. If t were to be equal to 1/2 of the year, the income would be 1/2 of $2,000. So this tells us the total income over a 10-year period will be the area under the graph from 0 to 10 here will be given by this definite integral here. So let's look at an example of this here. We're told that the rate of change of the income produced by a vending machine is given by this function here. And what we're going to want to do is find the total income produced to the nearest dollar during the second 5 years of operation. So the second 5 years of operation will be from 5 years to 10 years. All right, well, we know that the total income is going to be the definite integral of our function from 5 to 10 years. And our function is 5,000 e to the 0.04 times t. All right. What I'll do first is pull this 5,000 out front of our integral here. And next, notice that we have a composition of functions. So we'll let u be equal to 0.04 t here. This tells us that du over dt is going to be equal to 0.04, and therefore du divided by 0.04 is going to be equal to dt. Now in this case, I will change the bounds here. So if t is equal to 10 years here, plugging 10 into this t here, we'll get 0.04 times 10. So u will be equal to 0.4. Similarly, if t is equal to 5 here, plugging in 5 into our equation for u, we'll get u is equal to 0.2. So rewriting this, we still have this 5,000 out front. Our lower limit of integration is 0.2 and our upper is 0.4. And then we have e to the u du over 0.04, since dt is equal to du over 0.04. All right, so we can rewrite this by pulling out the 1 over 0.04 out front. So we have 5,000 divided by 0.04, e to the u du. All right, so on the outside here, we'll get 125,000. Then we'll have EU evaluated at the lower and upper limits of integration here. Doing so, we'll get 125,000 times e to the 0.4 minus e to the 0.2. And this is going to be approximately $33,802. So this is the total income produced during the second 5 years of operation. Now, in this example, we assume that the rate of change of income was given by a continuous function. In this case, we assume that the income is received in a continuous stream. So we assume that the rate at which income is received is going to be a continuous function of time. The rate of change is then called the rate of flow of the continuous income stream. So this brings us to this definition here. If f of t is the rate of flow of a continuous income stream, then the total income produced during the period from t is equal to a to t is equal to b is given by this definite integral here. Right? Now this is given by this figure here on the right. We have that f of t here is the rate of flow of a continuous income stream, and the total income is given by the area under this curve from this interval a to b here. Now, if we wanted to find the future value of a continuous income stream, we have to think about it in the following way. So recall from section 3.1, we discussed the continuous compound interest formula here. P is going to be our principal or present value. A is going to be the amount that we want to find, or our future value. R is the annual rate of our continuous compounding, and this is always going to be expressed as a decimal. And then T is given by time here in years. So for example, if money earns 8% compounded continuously, then the future value of a $2,000 investment in 9 years is given by this here. So we plug in all of our known information. We know we're starting with a $2,000 investment, so that's going to be our P. We know we're going to have 8% compounded continuously, so we convert 8% to a decimal, and that's going to be our R here. And then our time in years is 9 years, so that's our T there. Now, returning to the last example we looked at, where there is a trust paying $2,000 per year, we saw that the total value of the trust after 10 years is going to be $20,000, and that's going to be equal to the area under the graph of f of t here from 0 to 10, since we're looking at 10 years. Now, if at the end of each year you invest $2,000 you earned that year at 8% compounded continuously, the amount at the end of 10 years to the nearest dollar would be given by this here. So this is our compounding interest formula here for years 9, 8, 7, all the way to 0 here. But what happens here is that this amount underestimates the future value of the continuous income stream, because deposits are only made once per year, not continuously. The future value of the continuous income stream is actually going to be equal to the area under the graph of this function here from 0 to 10. Doing so, when we evaluate this, we see that we actually end up with $30,000 here, which is more accurate and tells us that at the end of 10 years, we will have received $30,639, including interest. Now, something to note here is that since you received $20,000 in income from the trust, the interest will be the difference between the future value and the income. So, the total interest would be given by this here, which is about $10,000 over the 10-year period. All right, so this brings us to this definition here of the future value of a continuous income stream. So if f of t is going to be the rate of flow of a continuous income stream over this interval here from 0 to t, and if the income is continuously invested at a rate r, compounded continuously, then the future value given by fb here at the end of t years is going to be given by this definite integral here. So let's look at an example of this. Using the continuous income rate of flow for the vending machine in the last example, we were given this function here. We want to find the future value of this income stream at 9% compounded continuously for 5 years. And we're going to find the total interest earned. So, in this case, we're just going to write down what we're given first. First, we see that our rate here is going to be 9%. And we know that we need to convert this to a decimal, so we know r is going to be 0.09. Similarly, our capital T here is going to be our years. We see that we're going to be compounding continuously for 5 years here. So capital T is going to be 5. Now what we can do is just plug the known information into our definite interval for FV here. Doing so, we get the following. We have e to the r times t out front, so that'll be e to the 0.09 times 5 out front. Then we have the definite integral from 0 to capital T, which is going to be 5, of our function f of t here, which is given by this. Times e to the minus rt here. R is 0.09, and we have t there. All right, so before we evaluate this definite integral, let's do some simplification first. For example, here we have 0.09 times 5, so this is going to become e to the 0.45. The inside of this definite interval here, we can also combine these two terms for e here. Doing so, we'll have e to the negative 0.05 t. So in this case, we are just adding these exponents. All right. Additionally, what I'm going to want to do is pull this 5,000 out front of our integral here. All right. Now we have a composition of functions, so we're again going to use our u substitution. So this tells us that du over negative 0.05 is going to be equal to dt. Now on the side here, we're just going to evaluate the indefinite interval here, so we don't have to change our bounds. So we have 5,000, that's e to the 0.45. Looking at the indefinite interval of e to the u, we have du over negative 0.05. Pulling that negative 0.05 out of our interval here, we'll have 5,000 divided by negative 0.05. So this is going to be negative 100,000. And we know that taking the indefinite interval of e to the u here is just going to be e to the u plus c. So with this information here, we can rewrite this guy. We know that this is going to be negative 100,000 times e to the 0.45 out here. And then e to the u, which is negative 0.05 t, evaluated at 0 and 5 here. Doing so, we'll get negative 100,000 e to the 0.45. We have e to the negative 0.05 times 5 minus e to the negative 0.05 times 0. Evaluating this is approximately $34,691. All right, so the next thing we're going to look at is called customers and producers surplus. So let P equal D of X. This is going to be the price demand equation for a product, where X is the number of units of the product that customers will purchase at a certain price of P dollars per unit. Now suppose that this P bar here is going to be the current price, and X bar is going to be the number of units that can be sold at that price. Now, looking at this curve here in figure 8, notice that the price demand curve here shows that if the price is higher than this P bar here, then the demand X is going to be less than this X bar here. However, some customers are willing to pay this higher price, and so customers who are willing to pay more than this P bar here, but who are still able to buy the products at P bar, will have saved money. So what we want to do is determine the total amount saved by all the consumers who are willing to pay a price higher than P bar for the product. Now to do this, we're going to consider this interval here, and looking back at this figure, that's going to be this small interval here. Now if the price remained constant over that interval, the savings on each unit would be the difference between D of C sub k. This is the price the customers are willing to pay and the price they actually pay here. So the difference of those two. Now since this delta x here represents the number of units purchased by consumers over the interval, the total savings to consumers over this interval is going to be approximately equal to this difference here. Again, this is the difference in the price consumers are willing to pay and the price they actually pay. Now notice this is going to be the area of this shaded rectangle here in this figure. And so if we divide this interval here into n equals subintervals, then the total savings to consumers is approximately equal to this here. Now notice, this is just going to be the sum of all of these differences times our number of units purchased by consumers over this interval. Now notice, this is the same as the Riemann sum for this interval here. Okay? So this is how we're going to define our consumer's surplus. So formally, that brings us to this definition here. So if this guy here is a point on our graph of the price-demand equation, P is equal to D of X here, for a particular product, then the consumer surplus given by CS at a price level of this P bar is given by this definite interval here. Now, notice that this is going to be the area between our P, our curve here, our P bar, and bounded by the lines x is equal to 0 to x is equal to x bar. So all of the area in this region here. Now, on the other hand, if P is equal to S of X is the price-supply equation for a product, then P bar is the current price and X bar is the current supply, then some suppliers are still willing to supply some units at a lower price than this P bar. Now, this additional money that these suppliers gain from the higher price is called the producer's surplus and can be expressed in terms of a definite interval, very similar to how we did for our consumer surplus. So formally, if this here is a point on the graph of our price-supply equation, P is equal to S of X here, so this is that point here on this curve, then the producer's surplus given by P of S, or PS at a price level of P bar is given by the definite interval here. And similarly, this is the area between our curve P here and P bar, bounded by x is equal to 0 and x is equal to x bar here. So all of the area in this region. Now, in a free competitive market, the price of a product is determined by the relationship between supply and demand, right? So if P is equal to D of X and P is equal to S of X are the price demand and price supply equations for a product, and if this point here is the point of intersection of these quantities, then P bar is called the equilibrium price and X bar is called the equilibrium quantity. Now, if the price stabilizes at the equilibrium price P bar, then this is the price level that will determine both the consumer surplus and the producer's surplus. So let's look at an example with both of these guys here. We want to find the equilibrium price and then find the consumer surplus and producer surplus at the equilibrium price level if our D of X is given by this here and our S of X is given by this here. So the first thing that we want to do is find the equilibrium quantity by setting our two functions equal to each other. So we have D of X is equal to S of X, so we'll have 25 minus 0.001 x squared is equal to 5 plus 0.1x. So what we can do here is rewrite this so everything's on one side. So we have 0.001 x squared plus 0.1x minus 20 is equal to 0. So all we did was add both of these guys to the side of our equation. Now, dividing every single term here on both sides of our equation by 0.001, we'll get x squared plus 100x minus 20,000 is equal to 0. And then we can factor this guy. We'll get x plus 200 times x minus 100 here. So this tells us x is equal to negative 200 and x is equal to 100. Now remember, x represents the number of units of a product, so x can't be negative. So this tells us our only solution is 100 here. Now remember, we just found the equilibrium quantity, so this solution here is given by our x bar. That is the equilibrium quantity. Now, what we can do is use both functions, d of x and s of x, to find our equilibrium price. We can plug this value for our x bar into either one of these functions. What I'm going to do is use this function because it's just a little bit easier to work with since we don't have this squared value. So the equilibrium price is given by this here. So we'll get 5 plus 0.1 times 100. And so this will be 5 plus 10, so this will be 15. Okay? So this tells us that our equilibrium price is equal to 15, and our equilibrium quantity is given by 100. Now, the second step that we want to do is graph this guy so we can get a visual representation of what's going on. In the interest of time, I've already done so for us. So here are our curves here. We have our supply equation here, S of x, given by this line here, and our price demand equation given by this curve here, d of x. And so we know by definition, our consumer surplus is going to be the area between our P bar, our equilibrium price, and our curve here, our price demand equation, from the lines x is equal to 0 to x is equal to x bar. This was x bar, that was our equilibrium quantity. And similarly, we know from our definition here that the producer's surplus was given by the area between our P bar here, our equilibrium price, and our supply, or our price supply equation S of x here, bounded by the lines x is equal to 0 and x is equal to s bar. Okay? So those are the shaded regions respectively. This is our customer surplus and our price surplus. So visually, that's what's happening here. This is our point, x bar, p bar here. All right, and we know to find these guys, we're looking at the area of each of these. So we're going to evaluate it by evaluating the definite integral. And we know from the above definition that this consumer surplus is given by this definite integral here. So our lower limit of integration was 0, and our upper limit is going to be x bar, which is our equilibrium quantity, which is 100. Then our price demand equation d of x was given by 25 minus 0.001 x squared. And we found our P bar, our equilibrium price, to be 15. So evaluating this, we'll get this definite integral here. So we'll get 10x minus 0.001 x cubed over 3, evaluated at these guys here. In doing so, we'll get that this is roughly $667. And similarly, we know that our producer's surplus is given by this definite integral here. So we have, again, our lower and upper limits of integration here. We know that our equilibrium price was given by 15. And then our price supply equation, S of x, is 5 plus 0.1x. All right, so we get the following. We'll end up with 10 minus 0.1x. This will give us 10x minus 0.1x squared over 2, evaluated at these guys here. All right, and in doing so, this gives us about $500 here. All right, so that'll be it for this video.